You know that feeling on a roller coaster, right? There's always that one highest peak, but there are also all those smaller hills and valleys. Well, today, we're going to give that feeling a name. We're diving into the language of graphs to find those absolute highest and lowest points, plus all the important local peaks in between. Let's get right into it. Seriously, just picture a roller coaster. There's that one moment, you're clicking up the big hill, and you hit the absolute highest point of the entire ride. But the ride isn't over, right? There are other smaller hills, other dips and twists. This is the perfect way to think about what we're talking about today, finding that one single highest point and all the other interesting ups and downs along the way. So, how do we take these ideas of the big hill and the little hills and turn them into something we can actually work with in math? Well, we need some clear, precise language to talk about these points, and that all starts with a couple of key definitions.
First up, let's talk about global extrema. When you hear global, I want you to think the entire ride. A global maximum is that one single point that's higher than any other. And a global minimum? That's the absolute lowest value. It's the king of the whole graph, no questions asked.
And then we have local extrema. The key word here is local, or sometimes you'll hear relative. A local maximum is just the top of one of those smaller hills. See, it's the highest point in its own little neighborhood, but it's not necessarily the highest point on the whole ride. It's a peak, but only relative to the points right next to it. So, look, it really just boils down to this one key difference. Global is all about the entire function, the whole shebang. Local only cares about its immediate neighborhood. You could say one is the king of the entire world, while the other is just the king of a small village. And honestly, understanding that distinction is everything. All right, so we've got the definitions down. Now for the fun part. Let's actually apply this to some real graphs. We're going to read the tracks of a few different roller coasters and pinpoint all their important features. Okay, so check out this first graph. You can see it has a clear start and a clear finish. Before I say anything, just take a look. Where does your gut tell you the absolute highest and lowest points of this whole ride are? Let's break it down. The ride kicks off at its lowest point. That's our global minimum right at the start. Then it goes up to a small peak, a little local maximum, but that's not the highest it gets. The true global maximum, the highest point of the whole ride, is actually at the very end. And this shows us a super important rule. You have to check the endpoints. They can absolutely be the highest or lowest points.
Okay, great. But, not all functions have a nice, neat start and finish. What happens when the ride just keeps going? See the arrows on this graph? That means the function goes on forever in those directions. So think about it. Can there even be an absolute highest point if the graph just keeps going up and up?
You got it. No way. Since the graph goes up forever on one side and down forever on the other, there's no single highest or lowest point. That means no global extrema. But we can still find those local hills and valleys. You can see a little peak there near the y-axis and a local valley a bit to the right.
Let's try one last scenario that kind of combines these ideas. This graph has a definite starting point, but then on the other side, an arrow tells us it goes up and to the right forever and ever. So what do you think that does to our maximums and minimums?
Yep, that upward arrow pretty much tells the whole story. The ride climbs forever, so there's no global maximum. And since there aren't any smaller hills on the way up, there are no local maximums either. But we do have a clear lowest point. The graph starts right at the origin and only goes up from there, making that starting point our one and only global minimum. Okay, we're getting pretty good at reading graphs that are already made for us. So now, to really make sure this all sinks in, let's flip the script. Instead of reading a graph, we're going to build one from scratch based on a few rules.
So here's your challenge. I want you to just picture in your head, or hey, even sketch it out on some paper. Can you draw a graph that has a single lowest point overall, has a smaller peak somewhere, but, and this is the tricky part, has no single highest point? Go on, give it a thought. How would you even start?
Okay, let's walk through it together. Step 1. Just draw a single point that's going to be your global minimum. Nothing else on the graph can ever go lower than that point. Simple. Step 2. Somewhere else on your graph, draw a little hill. Boom, that's your local maximum. Step 3, and this is the key to the whole puzzle, to make sure there's no global maximum, just have one end of your graph point up with an arrow showing it goes on to infinity. And just like that, you've built a graph that meets all the criteria.
So we can spot these points on a graph, we can even build our own graphs with them. But you might be sitting there thinking, Okay, cool, but why does any of this actually matter outside of a math class? And that is a totally fair question. The answer is, this is one of the most important ideas for solving problems in the real world.
Finding these maximums and minimums, these extrema, is really the heart of optimization. I mean, think about it. A company wants to find the exact production level that gives them the maximum profit. An engineer needs to figure out the design that has maximum strength while using the minimum amount of material. These aren't just points on a graph. They're the answers to real-world questions, representing the best possible outcome.
So every single graph tells a story through its peaks and valleys. It could be a story of profit and loss, of strength and weakness, of efficiency and waste. You now have the language to read that story. So the next time you see a chart or a graph, don't just see a line. Ask yourself, where are the peaks, where are the valleys, and what amazing solution is this trying to show me?